All right, thank you all for joining us today. Welcome to our session. We're going to discuss a little bit about hierarchical port binding and what is it, why you should deploy it. Real quick, just want to introduce ourselves. My name is Mark McLean. I'm the co-founder and CTO of Aconda.
I'm Nolan Lake. I'm the co-founder and CTO of Cumulus Networks.
Yep. So where are we headed today? What we're going to talk a little bit about is just kind of recap some Neutron basics for those not familiar with some of the details of Neutron. Talk a little bit about when you're deploying, how you're building and constructing networks, some of the design considerations. The real meat. What is hierarchical port binding? Why do you want to run it? What's the benefit? And then lastly, we're going to do a demo with hierarchical port binding with full open components and full open source. So. Neutron in 2 minutes or less. For some, again, it's an OpenStack talk. We have to show this logo. Remember, compute, networking, and storage. Networking binds the pieces together. Neutron's design goals, just in a real nutshell, is the ability to create rich topologies, be technology agnostic. This is what allows us to have multiple L2 backends, to have multiple implementations for layer 3 through 7 services. Make sure it's extensible so that if you want to support new technologies and new features, hierarchical port binding is an extension. Support advanced services, load balancing, VPN, firewall. And remember, the APIs are generic. So the cool thing about hierarchical port binding is from the user's perspective, they still see the compute API, the network API, and the storage API. So with Neutron, we can create kind of the basic topology and really create rich topologies within OpenStack. So this is kind of the recap of Neutron. So in terms of talking about building networks.
Yeah, so I mean, raise your hand if you've seen me rant about L2 and L3 in the past. All right, so I won't be boring too many people then, hopefully. So when you're building a network for in general, you have some decisions to make up front. Crucially, whether you're going to build an L2 network or an L3 network. And then more specifically, if we're building an OpenStack network, we need to decide how we're going to perform tenant isolation, to isolate traffic between the different tenants that might be running on the cloud. And so there's some common ways to do this. The kind of traditional approach is VLAN, and I'll talk a bit about that. But then there's kind of more modern approaches like GRE and VXLAN, and VXLAN in particular we're going to talk about quite a bit here. So I'm sure everyone's seen a slide that looks roughly similar to this before. So what we're showing here is you've got top of rack switches labeled access here, and those are actually just L2 switches. They don't have any L3 routing functionality. All they're doing is bridging frames. And on top of it, you have the aggregation tier. And so this is traditionally where you would run your kind of L2, L3 boundary. So this is going to route in between different VLANs and is also going to provide connectivity to these individual top of rack switches. Now what you'll see here is we're running in a configuration that's typically called MLAG, which stands for multi-chassis link aggregation. I'm not sure where the C went. And so this actually causes some problems, right? Cumulus has an implementation of this, and I'll even admit that sometimes it causes problems with ours. And the biggest problem is that this is proprietary. Every vendor has a different implementation of MLAG. And the other problem is you're still using VLANs, which means you're limited in scale to the 4,096, actually a little less, VLANs that you can use. And finally, and the biggest one, those pair of switches in the aggregation tier are absolutely crucial. So you have to have 2 of them. In fact, you have to have exactly 2 of them. And so the issue with having exactly 2 is that you probably don't have enough capacity there. You probably oversubscribe through this. And typical oversubscription ratios can be as high as 10 to 1, right? So if I'm talking to another VM or another host in the same rack, I can talk at full speed, 10 gigabits, 40 gigabits, whatever I've got provisioned. If I have to talk to someone in a different rack going through one of these things, I may only have 1 gigabit or 2 gigabits. And so that creates a huge east-west bottleneck. And so if you're deploying something like a network virtualization overlay or a distributed storage system, this is going to bottleneck that traffic pretty badly. So what do? We build an L3 network. So this, you'll notice now that there's a lot more of those switches in the second tier. Because this is an ECMP L3 network, we can have as many as we want, which means we can choose what oversubscription ratio we want. In this case, we've actually drawn it with no oversubscription. So in this topology, every rack can talk to, and a VM in any rack can talk to a VM in any other rack at the same speed as it can talk to VMs in its own rack. So now you don't have to know or care where the individual VMs are scheduled or located. But we still wanted that isolation, right? We still want isolation between different tenants. And many applications expect layer 2 connectivity between their VMs. And so what we do there is we use a technology called VXLAN. And the way VXLAN works is it's going to encapsulate those tenant L2 packets inside L3 tunnels. So they can traverse the layer 3 network as if they were just IP frames, because they are. And so the advantages this brings is now we can scale that IP network very easily, right? Because of it's an ECMP network. And all of those links are active. You don't have something like spanning tree protocol behind the scenes shutting off some of your links to prevent loops. And because you have much richer connectivity through the spine, you have much better failure scenarios. If you lose one of those spine switches, it's much less of a big deal than if you lose one of two, or God help you, both of your aggregation switches.
So now given the design considerations for building a network, how can we leverage that with hierarchical port binding? So what we first of all wanted to take a look at is kind of a quick primer again on like module layer 2. And so we're all used to seeing the Neutron reference implementation. You have multiple agents. You have layer 3 agents, DHCP agents, and a Neutron server. And inside of the Neutron server is where the ML2 plugin runs. It's basically broken down into two segments, a type manager and a mechanism driver, which has its own manager. And so type drivers, primarily what they are is they're for common interface for all segments, basically manages type-specific resources. So if it's VXLAN, it's VNI selection or VLAN ID selection. Type drivers are extensible, so you can create new types. So if there's a new format, you can add those in. You can configure those as a deployer. So the built-in types are the built-in types that you find within ML2. Local is just mainly for testing. It's basically traffic's never going to leave your test environment because you just get a bridge and it plumbs all the VMs together. Flat gives you access to the host to the underlying network within data center. VLAN gives you VLAN isolation, GRE, and then VXLAN. In terms of mechanism drivers, it's basically a common interface to all L2 backends so that when you're orchestrating the segments, it manages the specific backend communication. So commonly what you'll see is just the drivers have calls like create network or update network, create port, update port is kind of the interface. You can have multiple driver support. So Neutron supports multiple mechanism drivers. And so it's extensible. You can create new types of mechanism drivers. So as new hardware comes out or new solutions come out, you can plug them in. Yesterday, when we were talking, and Neutron now has 50 plus drivers, if you count plugins and ML2 drivers. So it's kind of crazy how extensible it can be. And then so you have both open and source closed. So real to meat is so when we talk about hierarchical port binding, what it allows you to do is take Neutron and to bind multiple network segments together. Previously, if you did this, you had to manually configure it, or you had to pick your tenant isolation type, and that was basically it. You couldn't have multiple rounds, and so you could actually build a hierarchy. So you can have a mix of segment types. So maybe you could have VLAN within the rack. You could have VXLAN across the tops between the TORs. And only in hierarchical port binding currently right now is supported with ML2 drivers. The monolithic plugins obviously are owning all the network, and so they work a little bit differently. It's available now in Kilo. This feature was released. The team really did a great job of getting it out the door. So for example, let's say we have two VMs, and the left VM, what happens with ML2 is so when the VM spins up, we create a port. Nova requests that the port be bound and wired in. And so in hierarchical port binding, what will first happen is that you go through and you take a step, and there's going to be a VLAN selection. And so in this case, we pick VLAN 37, which will then be selected. The next step in the binding is to say pick a VXLAN, a VNI. So we pick a VNI. If you notice here, because it's L3, we have full access here. And then coming down, we can have VLAN 55. The cool thing about hierarchical port binding is that because it's dynamic, you can actually have your physical networks limited per rack. And so you can have, and even go to further extreme and actually have VLAN segments dynamically allocated per port if your underlying hardware supports it.
So Mark did a great job of explaining kind of what hierarchical port binding is, but if you're used to traditional VLANs, or if you're kind of a little bit more forward-looking and you've configured VXLANs in your hypervisor, you may be asking, well, why don't I just have the VXLANs encapsulation happen in the hypervisor vSwitch? And there are a couple of reasons. The biggest one, and kind of what originally motivated this work, at least my interest in it, was we were having problems. We were having customers deploy with VXLAN, and they were having performance issues. They would have a fancy Xeon dual socket server with 2 10 gig NICs in it, and they would only be able to push 2 gigabits of traffic across the network. And so, we of course immediately started investigating. What we found was the NIC supports a lot of very cool offloads. The crucial one in this case is something called TSO and RSO, which is the important one is TSO, which is TCP segmentation offload. And so the idea is now the application and then the guest can give the NIC, maybe a multi-megabyte buffer, which then the NIC breaks up into individual packets. This obviously reduces the overhead quite a bit because you have a lot fewer interrupts coming down, you have a lot fewer descriptor rings being consumed by the NIC. But the NIC only knows the things that it knows, and so historically it knows VLANs. So it knows how to put a VLAN tag on the front of each one of those little packets it generates, but it doesn't know how to put a VXLAN frame on there. Now there are NICs coming onto the market that do support VXLAN, TSO in the presence of VXLAN, and so if you are careful and buy specifically those NICs, you don't have this issue. But if you just buy a 10 gig NIC today, you are very likely to run into this. So since we can use these dynamic VLANs coming out of the hypervisor, now all those offloads are preserved. But we don't want to use VLANs everywhere because of the earlier issues talked about around large L2 networks. So then, as Mark explained, we will do the VXLAN encapsulation in the top of rack. So now we can traverse that core, that densely interconnected core, as an IP frame. So we can take advantage of ECMP and routing protocols and all the other great things that you can do at L3. And the last thing is, Ironic is still relatively new, but it's a cool OpenStack technology to be able to bring physical servers into your virtual networks and have them collaborate with your VMs. But the problem is, if you're doing isolation and security inside the hypervisor vSwitch, with a physical server, there is no hypervisor vSwitch. So this allows you to then, instead of trunking a VLAN down from the VXLAN from the top of rack switch, you can actually just have the untagged packets come down to the server, which, as far as it's concerned, is just plugged into a normal L2 network. And finally, we can avoid the explosion of L2 table sizes, having to learn every single MAC of every single VM all over this network from the physical hardware, because all it cares about is the L3 addresses, which, since they are hierarchical in nature, are much fewer in number. And you'll be able to deploy this today, as we'll get into right here. And the last point, although most people don't run into this because it happens at very high scale, but the number of VTEPs, which are the VXLAN encapsulation points, scales with the number of racks now, not the number of hypervisors. So if you have 42 or 40 or whatever servers per rack, now you have a 40x reduction in the scale, so you're going to hit whatever bottlenecks in terms of scalability of the VTEPs way later at a much higher scale. So now we'll get into the demo.
So yes, so slightly cursed with live demos, so now the fun. So what's kind of inside our demo? We have, essentially our topology is we have 2 hypervisors connected through a pair of switches, and what we have is, so it's VLAN within, between the server into the switch, and then between the switches it's VXLAN. So basically our OpenStack release is the latest stable OpenStack release. We have ML2 drivers designed for hierarchical port binding. These drivers are the Alto Cumulus drivers. Like I said, it's VLAN between the server and the switch, and VXLAN between the switches. For layer 3 services, we have Aconda, which is running. So Aconda, if you're not familiar, is a Neutron L3 plugin. Implementation provides, in addition to routing, provides DHCP metadata and load balancing. It's fully open source, available. It is a Stack Forge project, so it basically functions as the rest of the OpenStack ecosystem.
And on the switches, we have Cumulus Linux. So I'll try not to get too close so that you don't pick up all the fan noise here, since these are designed to be run in a data center. But we've got on the bottom a Quanta LY9, which is an interesting switch that we just recently got support for. It's interesting because it's actually 10G base T, so you can connect your servers at 10 gig using just Cat6 twisted pair cabling instead of having to use SFP cables or optics or more complicated physical layers. And then on top, showing the flexibility, we also have an LY8, which is a more traditional SFP plus 48 10 gigs plus 6 40 gig uplinks. Crucially, these both have a Trident 2 chip in them, which means they can do VXLAN in hardware. And we'll be leveraging that. And the cable here, this is essentially the L3 network. It's just a single 40 gig cable in this deployment, but normally you would have 6 or 12 40 gig ports going up to 6 or 12 spine switches. But just carrying 2 of these heavy things around the world was complicated enough. So
should we dive into?
Yeah. So Cumulus Linux is a Linux distribution that, if you're familiar with Debian, will look very similar because it is derived from Debian, and we try not to deviate too much. All of your standard tools are going to work out of the box. So if you want to add a route, you can use IP route add. If you want to configure ACLs, use IP tables using the rules that you're already comfortable with. Similarly, to configure a bridge, you can use BRCTL. And I'll show you actually on the switch in just a second. Behind the scenes, we're actually using the Trident 2 ASIC in this switch to hardware accelerate the forwarding that Linux would have done in software. So much like if you used to play video games in the 90s, you would play your 3D game and it was very slow, and then you got your Voodoo accelerator or whatever. Now suddenly it looks the same, but it's way, way faster. So we're doing the same thing with the Linux software forwarding, but with the Trident 2 ASIC here. So if you look at it, it looks like a server, just one that happens to have an awful lot of NICs. So escape? Okay. So I can show you, I have here SSH'd into the LY9, so we can, ifconfig is officially deprecated, but I still use it. How do you scroll up on a?
Two finger,
okay.
2 finger on the mouse.
So you can see, all of the front panel ports show up as SWP number. So you're going to see all of those there, and then lots of them. And then you can see the VXLAN interfaces that the ML2 plugin created. So we have 3 right here. One is for the tenant network, one is for the internet, and the third one is the management network. So also you can see is the server is plugged into SWP1, which is the first switch port. So you can see we've created 3 VLANs on that. And so those VLANs are then bridged using standard Linux bridging into the VXLAN. So you can see here VXLAN 1002 is bridged with the VLAN 2001 on the front panel port. And so that's how they're all communicating here. Do you want to?
So we kind of talked how they're all connected at layer 2. Just kind of as a reminder, from the Neutron side, the logical topology is still the same. And so you see we have the router, we have 2 VMs, just to prove that they can talk to each other. Standard ping demo packets are going back and forth. And then but if we were to click in underneath, oops, timed out. As you see, the network type is VXLAN, segmentation ID is 1001. Also, if we take a look at the admin side, just to show you that the instances are running on different hypervisors, so that way you see that's going across and connected. So one's on NUC 1 and the other's on NUC 3. So I'll return back to this.
And so, there we go. So there's one piece we kind of glossed over here. If you're familiar with VXLAN, you're probably familiar with the BUM packet problem. And so BUM stands for broadcast, unknown unicast, and multicast packets. And so the fundamental issue is it's very simple in the unicast case to just basically learn MAC addresses. I learned that this destination MAC address lives on the VTEP that has this IP address. So if I see that MAC, I just send it out. Works very similar to L2 bridging. The problem is when I get a broadcast packet or an unknown unicast packet that I need to flood, or a multicast packet, that actually doesn't have just one destination. That could have many destinations. And so the solution we're using here today is something called VXRD, which is a VXLAN node registration daemon, and VXSND, which is the service node or replicator. So the service node is running on one of these NUCs. The same one is running the Neutron server and Nova and all the other kind of OpenStack components. And the registration daemon is running on the 2 switches because they're the VTEPs. And so what the registration daemons are telling the replicator is saying, basically, I am VTEP this IP address, and I'm interested in the following 3 VNIs. And VNIs are the numbers that identify a VXLAN segment. And so when a packet needs to be sent to everyone associated with a certain VNI, it's sent to that replicator, which will then replicate it to each VTEP that needs it. And so now, as far as the users are concerned, that packet did get broadcast just as it would on a normal L2 network. And this is open source. You can go to our GitHub and download it and play with it. We've only got one replicator running right here, but it supports running multiple for both high availability and for scaling the packet processing capability, as well as hierarchical replication, where you actually have basically one replicator per rack, so that you reduce the number of copies you have to ship across the core of the network.
So just to summarize, with hierarchical port binding, basically it's available today. You can deploy a fully open solution. You don't have to necessarily leverage or wait for proprietary solutions to be available. So in the situation we show here, this is the open solution is OpenStack, Cumulus Linux, Seconda, and then ONI-enabled switch. It works at scale. It actually allows you to go further. You can maximize the capacity of your hardware and your investments. And so lastly, thank you for your time. Any questions? If you could, because it's recorded, please go to the mic. Thanks.
Hello? Mm-hmm. The question I have is as far as the L2 population for, let's say, ARP, and the L2 pop mechanism driver today does like an ARP proxy. Is that the same behavior here?
The way we have it configured right now, we're not actually using L2 pop. And so it's, from the perspective of a VM trying to identify things like find an IP address, it'll send an ARP broadcast on the layer, the virtual layer 2 network created inside the VXLAN tunnels, and then whoever's got that IP address will respond with a unicast reply. Okay. If you were to add, you could, in theory, pre-provision these things and essentially turn on proxy ARP and have, avoid that broadcast traffic if you wanted.
Okay, excellent, thanks.
Follow-up, was there a reason you didn't go with L2 population updates over RPC channels to make it compliant with the VTEPs that exist today? And what happened to OVSDB, VTEP schema? Those kind of things.
As you might have seen when I was showing the Cumulus Linux switch, it's actually, the switch is not using OVSDB.
I know, but you can implement an OVSDB instance and communicate with everybody else that's using OVSDB schema. We're doing that on our devices today. I was just curious about why another proprietary L2 population service.
We haven't actually implemented a proprietary L2 population service here.
Okay,
so
well,
if you were
open,
to do that, if you were to try to do that, you would probably do it in the hypervisors and the OVS vSwitch there that's configured for VLANs, as opposed to trying to do it at the VTEP layer in the switches. Just because you want to short circuit those things as close.
Oh, I understand. I was just curious about why you did it that way and why, because we're starting to see interoperability between OVSDB, VTEP schema between vendors, even those that aren't Open vSwitch. They just implement an instance of OVSDB so they can do interoperability.
Oh, we implement the OVSDB schema. We don't use it in this demo. We actually did that for integration with some proprietary network overlay virtualization solutions. But in this case, since we could actually just run the Neutron code right on the switch, since it's just a Linux box, there was no need to have that extra layer in there.
Is there any help in port hierarchy to make sure that the VLAN that gets chosen on both of the integration bridges on either side is the same?
The VLANs don't need to be the same. That's actually how we eliminate the scalability bottleneck of the VLANs. The VLANs are essentially port local.
Is there any, so the service VM, where we're starting to talk about things like logical VLANs to allow VMs to be more than VIFs, to actually have VLAN tagging to the VMs, any help there?
That's essentially Q and Q at that point in
right.
Coming out, and we haven't looked into that. I mean, it's something we could do, definitely, but it's not something we've tried yet.
And then also from the driver side, you could have an ML2 type driver that actually understood VLAN selection and made sure it's uniform across.
Okay.
Yeah, that's an option as well. But for this particular one, we decided to maximize and go for VLAN ID selection per port.
Okay, thank you.
So this question is maybe a little related to the latter section of that questioning as a scale, really two related questions. What does it look like when you run out of VLANs? Mm-hmm. And is there any intelligence in the Nova scheduler to place or you have any plans to coordinate so that VMs that would be in the same network end up in the same place, so you don't end up in like a worst case scenario, every VM on every server in the rack is in a different Neutron network, and therefore you're burning
So we haven't really
thousands of
worried about
VLANs per rack.
because the VLANs are actually port local. So to run out of all 4,000 VLANs, you'd have to use 4,000 VLANs per hypervisor.
Oh, so you are doing Q and Q on the switch then?
No.
No.
Now, how are you doing, how many VLANs does the switch support? Is it 4,000 or is it 4,000 times 4,000?
It is around 4,000, but just because I'm using VLAN 100 on SWP1 for one tenant doesn't mean I can't use VLAN 100 on SWP2 for a totally different tenant, because the VLAN interface is a sub-interface off the port, which is then being bridged into the VXLAN by a separate bridge.
I'm just thinking if you have on the order of 40 or more hypervisors in a rack and on the order of 100 VMs,
Yep,
you
that
could
is-
be exceeding 4096 no?
No,
No.
You would be using, if you have 40, you said 100 VMs per hypervisor?
Yeah, I mean, just to make the numbers work
Yeah.
out, it seems like you could get in the ballpark in a rack or a pair of racks.
So in that case, you'd only be using 100 VLANs. You'd be using 100 VLANs on each port, and they could be the same VLANs or different VLANs. It doesn't matter. So, you know,
But if
unless
they're the
you-
same VLANs, don't they get bridged in the switch?
No, so
No?
so if you come from a traditional switching background, the assumption that a VLAN ID is really baked into, or is global, is really baked into the model.
Okay.
But the traditional Linux bridge, which is what we're using right here, a VLAN is actually just a sub-interface on a port. So if I have
Okay.
SWP1, which is the first port there, and I create a SWP1.100 interface, that's now VLAN 100 on that one port only. If I create SWP2.100, that's a totally different VLAN on a different port, and I can bridge them into different VXLANs. I could bridge them to each other if I wanted, or I could, bridge them to another, SWP.200. So then I'd have VLAN 100 bridged to VLAN 200. So it's extremely flexible.
Okay. All right, so but that's a hardware capability then, right?
So
That would
that's a
depend
hardware-
on what switches I have deployed in the network.
Correct, but every
Okay.
hardware, every switch we support can do that.
Okay. Most of ours are Cisco listed.
Hi, two questions. Firstly, you talked about working with Cumulus drivers. I'm just interested to know which other drivers are known to work, for example, OVS. And second one would be, could we have some links to configuration details so if we can replicate this?
Okay, so I missed the second question was you wanted the configuration
Yeah.
details?
The
What was
first
the
question is
one?
which other drivers, which other ML2 drivers, other than the Cumulus ones, can we try this with?
So,
Oh, the ML2 drivers? Yeah, I'll just
Yeah.
load the config.
yeah.
Oh, yeah. So see at the top, essentially we're running tenant network type, type drivers, local flat, and then the mechanism drivers is the Cumulus driver and just standard Linux bridge.
So nothing about bridge mappings or anything nasty down at the bottom then? Nothing about bridge mappings or anything nasty down at the bottom that you've changed?
Oh, yeah.
Oh, yeah, Mac stuff.
The devil's always in the bottom of those files, not the top.
So essentially, yeah, we just kind of, just for demo purposes, made it kind of restrictive just for a little bit of testing in terms of the VLAN dynamic range we could assign. And then the old VXLAN mapping, the local IP, if you know, it's turned off, so you can ignore that stanza.
Okay.
And then as far as just because we're using a Linux bridge agent, just telling that EM1 is our physical NIC.
Unbelievably simple.
Yes.
the goal.
Unbelievably simple. The other piece is the Linux bridge agent and the switch are using LDP to discover each other and relay that information back for Neutron, so the topology is kind of built dynamically.
Okay. So the first question was about other than Cumulus drivers.
Other than Cumulus drivers.
Yeah. So can we do this, for example, with just straight OVS?
Could you do this with, hierarchical port binding can, because the drivers, it's essentially, if you write drivers that are aware of it,
Yeah.
you can connect any number of segments together as long as the driver understands how to support and provision. In some cases, the driver might have to, if you want to make it fully orchestrate, have to set the bridges up and bridge different segment types together.
Yeah. So the specific question is, which other drivers are you aware of that would do that?
Oh,
Currently, right now in Tree, I'm not aware of any that have merged yet. There might be some in the ecosystem that are floating around, but when I was writing this, I basically took the original specs and test code and implemented it based on that.
So your sense is that this is going to be followed by other vendors as well?
I would assume this was actually contributed by other people in the community outside of us who were really driving it. Like the ML2 team really did a good job of adding this feature in the last cycle. The Cisco drivers are supporting it? Yeah.
Good.
Sorry,
I didn't know they merged yet.
didn't catch who that was. Who else is supporting it?
One of the Cisco people.
Cisco.
Cisco, they said that driver supports. Thanks, Bob.
My question is around the hierarchical port binding. Can we use it with L3 DVR facility, having a requirement where we need to connect multiple routing to external ports?
In theory, yes. I haven't tried it. So there probably will be some kind of minor bumps in the road, but if you're interested in trying it, definitely reach out, and I'd love to work with you on that.
All right. All righty. Oh.
Just wondering if this works with MLAG on a dual-homed server?
So today, no. It's being worked on actively as we speak. I'm sure if I checked my email, I would see some comments on that. So it needs a capability that we internally call VXLAN active-active, because what you would need is 2 top-of-rack switches that have an inner switch link between them, and then have an MLAG pair down to the servers. And then you need to terminate the VXLAN and then bridge it into the MLAG pair. And that last piece doesn't work right now in Cumulus Linux 2.5.2. It is coming in the next release, though.
Okay, thanks.
All righty. Thank you very much.
Thank you.